Thank you very much, Alpar. Thanks for the organizers for inviting me. This talk will be somewhat different in the sense that we won't be so much talking about HJB equations as much as Riccati equations. So it's going to be more along the linear quadratic games in the energy area. And I want to quickly acknowledge my collaborators here. Arman Kizilkal was my postdoc for a couple of years. Rabi Salab was my PhD. Arman is working for the AI industry. Rabi was my PhD student. He's postdocing at MIT. Quentin just finished his master's thesis, and he's responsible for the second part of the talk. It's a lot of what was done in his master's thesis. So I will first justify our interest in mean field games in the energy area. So I'll explain the motivation. Then we will be illustrating the control, the decentralized control that one can achieve using mean field games. In power systems. The special case will be controlling space heaters because they're attached to energy storage. I will develop two approaches which are relatively novel in the mean field context, in the LQG context. One is the integral control in the cost coefficient idea, which will be this first part. The second idea is inverse Nash. In other words, you're trying to achieve a certain Nash equilibrium trajectory, and you have to engineer a cost function that will lead you in a decentralized way to that result. There's extra material in the slides, which I will not cover, on electric water heaters. There's no time, and I'll move to my conclusions at that point. So justification essentially for our interest. Well, everyone has heard about green energy, renewable sources, and everything. Everyone wishes that we move towards a pollution-free sort of way of generating energy. The problem is both wind and solar are very capricious forms of energies. Sometimes they're there, sometimes they will not be there. So they may be there when we need, not be there when we need them, and they're there when we don't need them. So in that context, power systems have to constantly balance generation and demand. And so in that context, the ability to store energy is important. And of course, you can go some way with batteries and things like that, but it's expensive. It's not so great for the environment. So the idea of this research is you try to explore the possibility of using the distributed storage that's present in power systems when we all do electric space heating, like there's lots of it in Canada, or air conditioning, or if you do electric water heating, for example. So any kind of thermal process will have storage associated with it. And the interesting thing is that these loads, typically because they have storage, they are deferrable. For example, water heaters don't need to be being heated all the time. You know, if you have enough energy, you can go for a couple of hours probably without reheating. So the idea is to explore this deferrability to try to compensate for the variability of renewables. That's the basic idea. Now, what are the challenges in doing so? Well, we're talking about using, of course, with the agreement of customers, reaching out to their heaters, space heaters, reaching out to their air conditioners, reaching out to their water heaters, and send signals or do some kind of control and synchronize, coordinate all these loads so as to achieve a certain aggregate behavior, which will compensate for the variability of the renewable generation. Now, the classical way of doing control is to literally have one brain that observes everything, measures the signals, computes things, and then computes control actions. Now, if you want to do this, in that case, you have literally millions of control points to model, monitor, control. That would be lots of communications, but also, more importantly, severe computational requirements. So in the past, there were some approaches which were direct load control. And the idea was to send, let's say, 100,000 devices. You send the same signal, an interruption signal, for example, when you have insufficient power. And then you reconnect after a while, after half an hour, after an hour, or whatever. We'll see the problems with such control schemes. Now, in order to be able to make meaningful control signals, we need to have somehow an aggregate model. And the natural approach to do so in this context is inspired from statistical mechanics. In other words, you develop a stochastic elemental model which describes whatever processes you're trying to aggregate, let's say space heating, for example. And then you look at, these are essentially modeled as stochastic differential equations, and then you want to look at the aggregate behavior. That's what statistical mechanics works with. And so early on, we tried that approach. That was in the 80s. So here is a model that I'll be working with throughout the talk. A very simplified model of a home with heating. It could be air conditioning as well. So you have essentially a thermal capacity. It's a scalar model, a temperature process, and you lose heat to the environment if it's cold outside and you're heating. You have a heating source, which is electric. Here you have QH and MT. MT is the thermostatic state. So normally MT switching from 1 to 0, from 0 to 1, according to a dead band. X is a temperature process. X in is inside, X out is outside. And on top of that, you have a noise process, a Brownian motion, which accounts for all processes of heat losses and heat gains which happen in the home when you open windows, close windows, do cooking, start a TV set, or whatever. You're adding or subtracting energy. So mathematically speaking, this is a Markov process, essentially, with a continuous state and a discrete state. And we're interested in looking at an aggregate of these processes, and we're interested in particular in what the energy, total energy consumed at any one time is going to be. Now, BT is a signal that you can send. It's a 1-0 signal. If it's 1, you're letting the thermostat do the job. If it's 0, you're interrupting. And we'd like to, initially our intention was to try to build an aggregate model of what happens when you either let the thermostats work or when you interrupt the thermostats. And it turns out it's possible to describe the aggregate with two probability distributions, essentially. One for the on population, the temperature distribution within the population of on devices, the temperature distribution in the population of off devices, and these two are interacting. There's a drift because you're warming up when the on population. There's a rightward drift. This is the temperature axis. F1 is the density. F1 of xt is the density at temperature x at time t. F0 is the off population. And when you hit the thermostat, the deadband boundary, you switch from on to off at x plus. At x minus, you switch back from off to on. And so there's conservation of probability. You have two Fokker-Planck equations with conservation of probability, and that was our aggregate model. And with that model, you can anticipate what happens if you switch off, for example, all devices. Then essentially there's a virtual on population, but the thermostat cannot produce heat. So everyone is going leftwards, and the off population is getting empty into the on population. And when you reconnect power, you will get a recovery dynamics, and in general, you will get a peak of demand with oscillations until the system goes back to steady state. So this was done early on, but the problem with this is you have a limited dictionary to control those PDEs. It's only on-off signals. And the other thing is you have a fraction of customers which happen to be caught at the wrong time, which will be inevitably penalized if you're sending the same signal to a whole population. And the smaller you want to make this fraction, the less effective the control. It's like having a whole bunch of runners together. Some are fast, some are slow, but you want to have them run at the same speed. So you're bound to be inefficient. So we move on 15, 20 years and appear the whole theory of mean field games. So mean field games really, basically the way I see it, is a merger of two theories: statistical mechanics on the one hand, and dynamic games on the other hand. Okay, so the merging of the two theories was a very fruitful thing. And in the context of what we're trying to do, it is desirable first to have as much as possible, because we have millions of control points. We don't want to have to monitor them. So we'd like decentralized controllers, locally situated. We would like to minimize data exchanges between the users and the central authority or amongst users. And also we'd like to minimize the disturbance of users when applying these types of controls. So we're thinking of a sort of hierarchical architecture. I won't spend too much time on that, but at the power system level, there's a forecast of wind and solar generation. There's also a forecast of the component of the load that you're not controlling. And then there's the aggregate of energy storage devices that could consist that you want to be acting on. And so the idea is you need an aggregate model. And because we're talking about energy is additive. So an aggregate model typically is a mega model of the same type, but with the capacity equal to n times the capacity of individual homes, with heating elements which are n times the power of individual heating elements, and stochastic processes which are averaged. So you can get a sort of deterministic aggregate model with forecasts of wind, and you do some math programming to decide on a schedule of desired targets that you would like the aggregate to move to. It can be energy targets, it can be power targets. In general, it's often power targets. So it's like you're trying to decide what the power consumed by these aggregate devices should be at different intervals of time. So a subset of this problem, a building block of the solution, is to try to do tracking either of a constant energy level or a constant power level, an energy level over a certain amount of time, or a constant power level, or a certain mean target temperature for the devices. And this is what we're aiming at. Now, the reason why we focus on linear and quadratic control is we want the customers. We imagine they have microprocessors located at the residences. We want them to be able to carry out the computations. So it's important to have something that is relatively simple to compute. And the beauty of linear quadratic regulators is at least the control problem. We have a sort of, with Riccati equations and so on, we have an ODE type of solutions of these games. And the classical initial linear quadratic problem in the mean field games area was a rendezvous problem, whereby you have a whole population of agents and you're trying to have their states follow the mean state of the system, plus some kind of a bias. This cost function, which was our initial paper in 2003, was inspired by communications problems, but I won't go into that. But this is a classical quadratic with discount. Now I show this fish school essentially because I think it's a very good place to understand mean field games. The fish are like the devices that you're trying to control. And these are sardines, for example, which can move into big balls to pretend they're a large fish and try to discourage other large fish to attack them. And so this is highly synchronized and occurs with peer-to-peer communications. But you can think of these fish as having cost functions, and each one trying to produce a decentralized control. And the goal is to get the fish want to follow the centroid of the school to stay together. And so in some sense, our problem is to get, to build cost functions to be able to have the individuals in the population, the statistical behavior of the population match a certain desired behavior. This is really the problem. And so we're looking for prescriptive linear quadratic mean field gain, meaning it's not the normal game setup. Here we're choosing the cost function, but we're choosing it in a way to accommodate the customers, but at the same time to have the coordinator meet its goal. So the whole challenge is to build a cost function that will achieve these purposes. So games are interesting in that aspect because they are a natural device to enforce decentralization. Each one is looking at their own cost function. Each one is looking at their own view of the world. And in mean field games, interestingly enough, the law of large numbers allows individuals to think of the mass as having a independent behavior, which is a given behavior. Of course, how you compute that is a fixed point ultimately, but there's a decoupling, which is very nice to exploit, and there's some measure of predictability. The practical benefits is that the resulting control laws are feedback, which can be computed in an open loop manner, which means you can reduce communication requirements. Of course, you cannot go indefinitely open loop. You need things, your models will drift away from reality, but it allows you to do piecewise open loop kind of control. And unlike the direct control that I was referring to earlier, which is from the power system to the devices, here the control is synthesized locally. So each device is locally controlling itself, which means that if you have mismodeled the system and the device, you're computing a control that is taking you out of your comfort zone, the device out of its comfort zone, it can opt out. So because it's observing the local state, the device can quit the control scheme and remain within its comfort zone. So these are two major advantages of the approach. So let's see how this works when we apply this idea back to that shell model, capacity, losing heat to the environment. Now we're going to make two changes to the model. The first one is we're going to say the thermostat is the default mode. But in order to apply these mean field gain controllers, we're going to have a continuous control. So we're going to make the heating a continuous process. That in some cases, it's already possible. It's naturally possible. In other cases, it's a technological change. The second thing we're going to do, because we're building up to a cost function that is that will try to preserve the comfort of customers, we're going to consider the control, which is the heating. We call it U in our terminology, in control theory terminology. I know that game theorists use a different terminology here, alpha, different notation. So the control now, we're going to say we are giving the devices the power that they would need to stay at the temperature they were sitting at the beginning of the control horizon. So we're saying, look, you can get that power for free, and we're going to penalize any deviation above or below that power, because this is going to cause customer discomfort. So we redefine the control, the power, as a deviation from the quiescent initial condition in each one of the devices. We're also going to and this is an agreement between the power system and the customers. The customers define a maximum temperature that they will tolerate in their homes and a minimum temperature. Now, the maximum is 25, the minimum is 17. I know this is cold, but and so one should imagine this is the problem we're studying. We're actually trying to control the energy expenditure, and so we are at some mean initial temperature in a collection of, say, 100,000 devices, and we're trying to over a period of time, we'd like to remove some energy out of these devices. In other words, we're not going to furnish an energy these devices would have normally asked for. And so if we remove energy, the temperature would go from some initial value, say 21.5 degrees, and we remove half a degree on average, that would get us to 21 degrees. So we have a temperature tracking problem, and we'd like to do that in a decentralized way. Now, the first idea that comes to mind, and it is really decentralized, is to do simple temperature tracking. So I'm going to decree that I want all the devices to go to their target temperature. So I'm going to create a cost function, which is a standard tracking function, quadratic. So we penalize xti minus y squared times a coefficient here, which means we're trying to send all the devices to the same desired mean temperature. But you realize this is maximal disturbance, because these guys are moving all the way from this 23.5 all the way to 21. And these guys are moving from 19.5 all the way to 21. Everybody's moving maximum swings, and these guys are undoing what these guys are doing. Okay, so they're fighting each other. It's not a great idea. The next cost function is more complicated, but the idea is to have all the devices move in unison. They move all in the same direction. Either they increase their temperature or decrease their temperature. In this case, we're trying to decrease temperature. So we're going to send the devices to the lowest temperature tolerable. So 17 in this case. So we create a penalty term, which will try to push all the devices towards that lowest temperature. And two other terms in the cost function. This is what the coordinator wants, but then the individuals want. They say, "Don't bother me. So keep me at the temperature where I was." So this is penalizing any deviation from initial temperature with a square term. And remember, the control was any deviation from what I need to stay where I was initially. So again, these two terms are trying to favor the comfort of the customers. This term is trying to get the coordinator to obtain what it wants. Except the novelty here is that the QT term is no longer an arbitrary time varying trajectory, but we use here integral control. So we are integrating the error between the mean temperature of the group and the target. So as long as the the mean temperature, the empirical mean, is far from the desired target, this quantity is being integrated, this error. X bar is initially above y, so we're integrating. G in general is a monotonic function, and so it will increase with this difference, and we are taking absolute value, and normally there's a lambda coefficient multiplying, a positive lambda coefficient multiplying this integral. I omitted it here, and so this is kind of mechanically looking for the pressure field that you need to establish so that ultimately the mean goes to the target, because as long as the mean is away from the target, this quantity is increasing. And so the pressure to move towards the minimal temperature is still on and keeps increasing. Okay, so that's really one novel idea, one key idea here in these formulations. So, and of course, you could use either a linear operation or a nonlinear operation, but I won't dwell too much on this. We'll just focus on the linear integrator here. Now, as I said, the novelty here in this scheme is you're using integral control in the cost, where integral control is a well-known device in classical control theory, but it was never used inside a cost function. How do we analyze the situation now that we have this set up? Well, the X bar, the empirical mean, because the numbers are very large, the coupling of devices, the only way they couple is through the empirical mean, which acts on that QT. So the empirical mean, and that's what the mean field game theory tells us, is going to converge to something stationary, something not stationary, but deterministic. And so you have some QT trajectory. So you have essentially a deterministic linear tracking problem, linear quadratic tracking problem with some QT that you initially don't know, but you can assume it's a continuous function. And you can write the equations that allow you to compute the optimal control. So each agent is going to react optimally to that given trajectory. And because the agent is hit by 1 over n, its contribution vanishes as n goes to infinity. So the agent is not affecting the mean trajectory. So you get this system of differential equations. The first one is a Riccati equation. The second one is a linear differential equation once you compute the Riccati evolution. You're going to get a linear Fi control, which is a pi t times the state plus some open loop st term. You plug in this feedback control law into the individual dynamics, you average these dynamics, and you get the dynamics, the closed loop dynamics for the mean. The beauty, again, in this linear context is you don't need PDEs. Normally, you would need a PDE here to describe the behavior of the mean. You would need a Fokker-Planck equation. Here, it is simple linear equation, and the whole system is collapsing. The whole population is aggregated into a single differential equation. Now, this X bar is integrated to produce the pressure field QT through the integral control. So you can see what we need to do now. We start with some guess of what QT should be. We compute the solution. This QT feeds into the differential equation of pi t, which feeds into st, which gives us a new X bar. This X bar is integrated, gives us a new QT. So you need this QT in to be equal to this QT out. We're looking for a fixed point. So instead of solving a fixed point for a Fokker-Planck and an HJB equation, which is much more complex, of course, we're looking for a fixed point for a system of nonlinear ODEs. Okay, and so the big question now is, given that system, does there exist a fixed point? I mean, do we have a hope to? Can we guarantee a fixed point? And we're going to go through the Schauder route in order to establish the existence of a fixed point. We're going to be working with X bar rather than Qt. So we start with some X bar, and then we carry out all the computations. We get a Qt, and ultimately we get a new X bar, and we want a fixed point to be on the X bar. The delta of X bar is this integral operator. The T operator is the one that results from Qt back to X bar. So there's a composition of two operator, a tau and a delta, and we'd like to see if we can establish that this will produce a fixed point. We'll have a fixed point. Well, we're going to work, I think there's a typo here, we're going to work with a space xt, which is continuous functions, which are bounded between the maximum and the minimum allowable excursions. It turns out, so we look for a solution in the space of continuous functions, but it turns out that if you use the infinity norm, the soup norm, on that space, that Banach space, you can show that you can find counterexamples, in other words, initial guesses, which will produce a discontinuous X bar. And so this norm will not do the job for us. So we need to use for that problem, and that's why it was a discounted problem, we need to use a norm which is somewhat different. It's a soup norm, but it's a soup norm of a discounted version of the mean trajectory, discounted by e to the minus kt, with k. As it turns out in the result, it'll have to be to satisfy certain constraints. Okay, so this is the k, this new soup norm, and this soup norm allows, in fact, runaway situations. That is, what happens is we're going to get existence of a fixed point, but it could well be that it's a bad fixed point. In other words, it could be a fixed point where everybody crashes at the lower edge of the allowed temperature. So you miss your target and you keep going. And in that case, Qt goes to infinity. But the point is it's exponentially bounded. Okay? And in that case, under these constraints, one can show that this space G is invariant under that under combined operator, and Schauder fixed point allows to guarantee existence of a fixed point. Another interesting result, of course, which is we were dealing with an infinite population in theory, but in fact, we have a large number of devices. It's not infinite. It's possible to show that if you use the infinite population dictated solution and you apply it to the finite system, you're going to have an epsilon Nash equilibrium with epsilon going to zero as n increases in general. It's a 1 over root n result. In that case, we just proved simply it just goes to zero. We didn't put an order in the result. But this means that if individuals would like to deviate, they cannot improve more than epsilon relative to what if everyone else is using the strategy obtained based on the infinite population solution. And now, as I said, this gives us existence, but it doesn't necessarily give us a desired fixed point. We'd like in practice to always converge to the target. So we we find a compromise here, which is essentially, I won't spend too much time trying to explain how we do things here. But essentially, we're going to impose to look for fixed points only amongst trajectories that land on target. And as it turns out, the QT candidates that will land you on target must all share the properties that in the steady state, that is, as t goes to infinity, the QT becomes constant, a constant called Q star infinity, which can be exactly computed based on the desired target and the properties of your cost functions. So we know everyone has to, all the allowable QTs must land on that. And so we create, in fact, two pressure fields. I'm going to call the QT a pressure field because this is what's driving the temperatures to the low end of the allowable limit. And so we're going to take a high pressure field, which is discontinuous, but it doesn't matter. It's going to produce a continuous response. It's a high value, n times Q star infinity. That's the high pressure field where n is high, on an interval 0 t0. And then past that interval, we're going to send the value, we're going to send it to Q infinity, okay? So very high pressure for a short interval of time, and then we send back to the value that it should be at during steady state. So we have a high N, high pressure field, and a low N, and both of them will induce a response, which will give you the high N, the high pressure field will give you a low mean trajectory, lowest mean trajectory. The low pressure field will give you a high mean field trajectory of temperatures. And then we're going to look for convex combinations. Both of these actually are landing on target by construction because of that value Q infinity that we impose in the pressure fields. And we're going to look for convex combinations of these two extreme trajectories. That's essentially what we're doing. And within that family of convex combination, we're going to look for the trajectory that is the nearest Nash equilibrium, the nearest Nash fixed point, the nearest fixed point, if you will. And that will give us an approximate desirable fixed point. That's the algorithm, essentially, that we came up with. So here is the result of simulations with that kind of algorithm. So we start with 200 heaters with initial distributions from a Gaussian, mean 21 degrees, variance 1. We want to decrease 1 degree over a 3-hour control horizon. And we're going to compare the classical tracking solution with this modified cost, with this prescriptive cost solution, which involves integral control. So essentially, I'm going to zoom in here a little bit. I hope this shows it well on the screen. I don't know. So this is what the LQG control provides. You can see sort of an exponential decay, but we know that the problem is that the temperatures are fighting each other. The devices are fighting it. Oops, no, sorry. Let me see if I can do that again here. Okay, LQG control. Okay, this is the mean field control. This is the response. In fact, there are many curves which are superimposed here. There's a curve, the red. I can't move my mouse here. The red line on the right indicates actually the input trajectory, which produces the nearest Nash. The yellow is the output trajectory, to that nearest Nash, and you can see they're practically on top of each other. So it's a good fixed point, if you will. The target is in violet or whatever color it is. And the empirical average is blue, but it's superimposed on all of this and you don't see it. Okay, so we're doing well. Within 1/2 hour, we're getting to the desired position. Okay, these are the sample path associated. So you can see this is the mean field dictate. You can see everyone is moving in the same direction. There's a bit of undershoot, but by and large, they're all collaborating in the same direction. And there's a certain fairness in the sense that this is a progressive tax, namely the highest initial temperatures are producing the largest contribution because they're losing more energy than the lower temperatures. So this is trying to accommodate different users according to their initial conditions. You look at the LQG control, it's bothering everybody, and everyone is having these huge swings. So this is definitely, from an engineering point of view, a more desirable solution. This is what you get when you use a nonlinear integral control. I won't dwell too much on that. Okay. Now, interestingly enough, the integral control, all of these computations were carried out in open loop, but it could very well be that you have mismodeled the system. For example, you may have underestimated or overestimated the initial mean. You may have underestimated or overestimated the ambient temperature. So here is a situation where you have the actual mean, which is 21.5, but you think it is 21. The ambient temperature is -11, but you think it is -10. So when you do your open loop calculations, you get to a point where you can see that the target is not being reached. So you can switch at this point to if you have the possibility of observing the mean power, which is consumed by these devices, that's still an issue. But if you could observe it and stick that value into the integral that produces QT, then you could be sort of estimating online what the QT should be. And what we see is that there's a transition phase, during which the QT is, the pressure field is using the observations to adjust itself and ultimately catches up with the exact value. So this integral control is adding some robustness to the system if you have the possibility of observations. Now, the second part, and the last part actually, is a power control problem. Actually, what we've described may have been a power control problem. We've converted it into an energy control problem by saying, you want to reduce power, that means you're going to reduce energy over a certain amount of time. And temperature is a proxy for energy. So that's a target, that's a temperature target problem, target tracking problem. And this is what we solve. But you may still want to have constant power, average power consumed by the devices. And the previous approach does not solve that problem. So there's a second approach, which is called inverse Nash. And here is the idea. The idea is to essentially assume that the shape of would be desirable Nash equilibrium trajectory. In fact, it could be the mean. In our case, it's the mean. But in general, if you have a collective control problem, it could be some statistical property of the distribution, the trajectory of that, a quantile, for example, the variance, some higher order moment that you would like to have following a given desirable trajectory. So you postulate that this is your equilibrium. You identify this trajectory, you postulate that it's your equilibrium, and then you look at the essentially so in our case, we want to have a constant power target. So we want the devices to consume a constant mean power during, say, half hour, 1 hour. So we inject this mean power into the dynamics of individual devices. In the dynamics of the mean, it's linear. We can produce the mean trajectory. And now we take this mean trajectory and we go back to the fixed point equations that we saw earlier. And the
Sorry,
idea...
Roland, you have 4 more minutes.
Okay, great. I'm wrapping up. Thank you. So this QT is what I need to compute, and so I look at the essentially the mean dynamics, as I said, by looking at the mean equations and applying constant power to these to this mean temperature dynamics, and then we look at the optimal control equations. Affine feedback, Riccati equation, and this is the open loop part of the control. We average these equations, and then we look at exactly the equations I was showing earlier. These, by the way, these Riccati equations, they need boundary conditions. We're going to set the boundary conditions at the end horizon to be exactly what we need the pressure field to be for to get that, because temperature is going to converge to a steady state if power is constant, and the steady state is when you balance heat with the losses. So we know exactly where we should be going at capital T. We impose this as a boundary condition. This gives us a boundary condition on the Riccati equation and also on the open loop part. And given that, we look at the system of fixed point equations. It turns out we can substitute the pi t equation into the beta t equation and get this nonlinear differential equations driven by the derivative of the both the mean trajectory and its derivative, but these two are known signals. So you get a known differential equation that you try to solve. And of course, you have to be able to solve this. And Riccati equations are known to produce finite escape times under some conditions. So essentially, in our case, if Qt remains positive, then we don't have finite escape time. So we can solve for pi t. And once you know pi t is just a matter of substitutions, and you get the pressure field that you need. And so this is how we carried out the computations. We're back to that example with 200 heaters, but then we want to decrease power by 5%. Okay, on a 5-hour interval, but actually we're going to get there quickly. So this is the target power, and you can see how quickly you can zoom in on the desired power level because we have a pressure field that has been computed in order so as to achieve that mean power consumption. So that's an idea, and this is what the trajectories look like under that. Again, you see a principle of the richest, a sort of progressive taxation, with the richest making the biggest effort, the richest in energy making the biggest effort. So I'll go to my conclusions. I'm wrapping up here. So prescriptive mean field gains are actually a natural approach for this load management. It exploits the predictability. It minimizes communications, and it's flexible tool. It's a very flexible tool because by playing with the weights, you can stress this or that aspect. Its weakness is that it overly relies on a correct statistical description of what the device statistics are. And also, I've worked mostly with a homogeneous population. There is some, in the inverse Nash approach is tolerant to some diversity, but I didn't present that. What's future work? It would be important to develop online model parameter identification and adaptation algorithms. As this approach gets implemented, lots of data is going to be gathered, and you can improve your models. It would be interesting in general in collective dynamics to exploit fully this inverse Nash approach. And then it becomes a question of what kind of signals can I track by simply building, adjusting my cost function. It's kind of an existence or an invertibility problem in general. It would be interesting to explore that. The constraints, the local constraints of, we haven't considered saturations and various things. What does, how do you solve mean field games when you have input constraints, for example? I think it's an interesting question. And then maybe cooperative solutions. Right now, we've designed essentially non-cooperative solutions. Thank you very much.